Okay, good evening. Our today's speaker is Georgy Sharygin. Gosha, you're welcome. Please begin.
Okay, just need some time to put on this device.
Значит, вот это куда угодно.
Harness, right? Okay.
Это важно, это тоже куда угодно, лишь бы вот это, значит, колокольчик был
Just a moment. It should go in my pocket. This goes to my pocket, and this, just let me know, it's somewhat strange. I don't know what to do with this. Something like that? No. Because okay, it will be like this. Is this okay? Do you hear me?
Yeah, I think yes.
Okay.
Okay.
Yeah, thank you for your invitation to make a talk. So today my talk will deal with something new. Usually I talked here about integrable systems, first of all, Toda system, and also about argument shift method and its quantum analogs. So today I'm going to talk about something different, totally different, although I believe there is some relation between what I talk here, whatever I'm going to talk about, and integrable systems, at least. We'll see. So I'll probably not get us to that point, but at least I'll explain what to do to go there. So first of all, let me recall the paradigm of an algebraic geometry. So since 1960s, about so, 1960s, modern algebraic geometry is usually phrased, is often phrased in terms of rings rather than in terms of spaces. So if you have a space A, it would be some algebraic variety or something like that, then in algebraic geometry, it is a kind of general nonsense that this space is uniquely determined by its algebra functions. So have a space A, X, and you can substitute it for its algebra functions, regular functions, if you know, if this notion is defined in that case. If this, then the space can be restored as the space of characters on the algebra functions. Well, it's called the spectrum, maximal spectrum of this algebra. So the spectrum is the space of all maps from homomorphisms from OX into the ground field or some other ground field. So it depends on the definition. Actually, I'm not going to reproduce it here. I'm not prepared to do this. But you can substitute some ground field on the right, and then you get the spectrum as the space of all homomorphisms, algebraic homomorphisms. Good question. It's actually, let it be local. Yeah, there are lots of actually modifications of this definition. So I'm just giving the most rough description of what I'm going to talk about. So actually, you can substitute various points. You can speak about varieties defined or various schemes of various, Archimedean, non-Archimedean, so on and so forth. But yeah, there are lots of details. This is a very large science developed since 1960s. By such renowned and famous people as Grothendieck, Deligne, Mumford, and many, many, many others. So it's very hard to describe them. It's impossible. So on the other hand, if you speak about what they call noncommutative geometry, so the science of noncommutative geometry emerged somewhere around 1985 or about so. And at first it was due totally to the efforts of Alan Kohn, who phrased it completely in the terms of sister algebras, topological and other topological algebras. So it was no such freedom as we have here was allowed In that case, there was lots of analysis, lots of efforts was done to make sense of definitions which are totally right here. And this non-commutative geometry survives, and it is even in modern, in the classification of math science classification, if you look for it, you will see non-commutative geometry à la Con. There has a special item there. That's what we call non-commutative geometry à la Con. But somewhere in 1990s, 1995, about so, there appeared a series of papers by Maxim Kontsevich and Alexander Rosenberg, who developed what they call algebraic non-commutative geometry. So in that case, they came up with the following idea of what you can substitute for the spectrum of a non-commutative algebra. So how would you have a non-commutative algebra? Non-commutative algebra. Of course, if you just look for homomorphisms from this algebra into a field, then you associative, yeah. Yes, I'm sorry. All algebras in this talk will be associative by default. The space of all maps from A to fields or to any other commutative algebras will be very poor, almost nothing there. So you cannot use it to define its corresponding space of points. So what you can do here, on the other hand, you can recall that, well, let's put it this way. Categorically speaking, the algebra of modules, the category of modules over matrices is equivalent to the category of modules over the algebra which stands inside. Is Morita equivalent to the category of modules over mod over A. So if we are on this in category, we can say that there is no difference between this algebra, or for anything you can take a field, and the algebra of matrices with coefficients in this field. So it makes us, it gives us the following idea. It allows us to consider the non-commutative counterpart of this construction of spectrum. Namely, we say that representation spaces of A is just the space of all homomorphisms from A to the space of matrices, and by matrices with coefficients in the field. So this sequence of spaces for all n, natural n, is kind of counterpart of the spectrum of the algebra in algebraic geometry. So, huh?
Yeah, I'm sorry. I'm a little bit lost.
It's kind of it's kind of the idea why we need to identify K and this space, because it's, well, categorically speaking, yes, but something equivalent to it, but larger. Yeah. So yeah, that's just the idea, just the motivation. So this non-commutative algebraic geometry still exists of this different. Yeah. Yes. So this is what we call non-commutative algebraic geometry, or algebraic non-commutative geometry. I don't know what is the order of epithets here, of adjectives. Since that time, it's been, I couldn't say in the focus of many people, but still there exists quite a bunch of papers and results concerned with this idea. So that's what I'm going to say. So that's one motivation. That's one motivation for my talk, for this whole definition which I'm going to give. Namely, we want to consider algebra A, which is non-commutative but associative, and we want to define some kind of analog of Poisson structure on this algebra. So there are two ways to do it. One is naive, which actually gives pretty little. Naive way is just to say that it is a map, bilinear map from A, tensor A into A, which satisfies all the standard conditions. So it should be skew symmetric. It should satisfy Leibniz rules. Well, actually, left and right, but it's skew symmetric, they are equivalent. And should satisfy the Kobe identity. So that's a very naive way to define Poisson structure. And it gives pretty little, especially if the algebra is simple. Well, if it is matrix algebra, for instance, is the matrix algebra, then it is well known that there exists only one such map. Namely, if you take x and y, then it should give you nothing else than the commutator modular, well, but multiplied by some scalar. Just this, only this. In fact, one can prove. I think it's, I even know the reference, thanks to, yeah, precisely. I was going to give this reference, Volodya pointed out to me, that actually one can prove this not only for matrix algebras, which is well known by physicists, but also one can prove it for what so-called prime algebras. So prime means that if you have two ideals, I and J in A, then their product is non-zero. For any algebra with this property, there exists only one sort of Poisson bracket. Well,
For any two ideals.
yes, non-zero ideals, of course. Yeah. No divisor, yeah, or no divisors of zero in ideals, in the space of ideals. Mm-hmm. Yeah. So as you see, there are lots of such algebras. Of course, lambda here can be now taken from the center of A, but it's just an easy generalization, not very important. So there exists very little example. The quantitative example is pretty small. So that's the second motivation. We want to work with a non-commutative space and consider some Poisson structure on it, but this kind of Poisson structures is non-existent virtually. So we want to give some generalization of this notion. And if we now recur to this principle, we get some guiding idea as to what kind of conditions we need to impose. The idea is pretty simple. So this space, especially if A is finitely generated, is an algebraic variety. Maybe singular, maybe not singular, but it's all algebraic because you can actually choose the set of generators, A1, AK, generators of this. Then you can send each of them to a matrix, X1 through XK in matrices. And then the only condition you will have is, is the condition that these matrices satisfy the same relations as these elements. So these relations will give you a series of equations, polynomial equations, satisfied by the matrix elements, and it's almost by definition algebraic variety, even a fine algebraic variety. So the guiding principle is as follows. We have an algebra A. We want to introduce a Poisson something on this algebra. And the condition that this something should satisfy is that this something should induce usual Poisson structures on these algebraic varieties. That's one of the main principles of noncommutative algebraic geometry. If you want to introduce a noncommutative analog of something or some structure on noncommutative algebra, then this analog should induce classical structures on the representation spaces. Yeah, that's the, what did I say? Correspondence. You can call it correspondence. I didn't know. Yeah, maybe. They call, Joseph Simonich said that this is what they call correspondence principle in physics. Yes.
It is called usually representational functor philosophy.
Yes.
Empirically means that if you want to get something good in non-commutative algebra, you should have something good on the representation space.
Yeah.
Considering okay.
Yeah, you can put it this way as well.
If you consider non-commutative algebra like one-to-one.
Yeah. Okay, so there exists. So now I'm going to speak about non-commutative analog of the Poisson structure. There exist, in fact, several different definitions, and I'll give a couple of them after I give first the definition due to Michael van den Berg. So Michael van den Berg came up with this definition about 2004, I think. At least his paper, I think, dates to 2006 now. Six about that. I think his paper on archive is dated by 2006. Yeah. So about that time.
But this definition, it is a kind of despair, because before there was a very natural definition with a very small success of application.
Yeah.
But definition was very good. It's a definition
of
pink shoe.
Pink shoe. Yeah.
Yes. So on
Purely
homological.
Yes. But after Van den Berg,
it would be interesting to
yeah, it should be. Actually, I really would like to know more about this. I know the definition by Van den Berg. I know the definition by Crowley-Bovey, and his more or less equivalent.
The definition of pink shoe, it's a definition that generalizes Why?
He helps. It's not a
common. And I think for Krasильchik, it would be much more interesting because this definition generalizes the property of zero Poisson condition for Scout and main case bracket.
This actually also has this kind of zero Poisson. Yeah, it has some analog. Probably not going to speak about this very accurately. Okay, so what did Van den Berg suggest? The idea is pretty simple. What was the main obstruction for the usual definition of Poisson bracket in non-commutative world? It is that when you use Leibniz rule, you need to work with left and right module, right? But you also have left and right arguments inside the Poisson bracket. So somehow you need to provide that the left and right module for these two arguments do not interfere with each other. somehow. You see, you need to take the left model structure here, put the argument here, then you need to take the left model structure here and put it on the left here. But you can also do this in opposite direction, in opposite order. And then you need to have that AB should be equal to BA somehow. And that's too much, actually.
For the non-commutative case.
Yes, in a commutative case, of course. In commutative case, there is no problem. So what now he suggested? He observed that when you work with a tensor square of A, and we in fact have not one bimodal structure, but actually two, even more if you want, but two are distinct, and they do not interfere. Actually, yeah, more, four. But yeah, natural, of course there are four, but two are sufficient. For us, two are sufficient. So the external, when you multiply everything from the left and from the right as it stands on the blackboard, at the blackboard. And internal, when you multiply everything inside this bracket. And they do not interfere with each other. So you can actually take advantage of this and give the definition in terms of these two brackets, of these two structures. And this is the definition he came up with. So first, a bracket is a map from this tensor product to itself. It satisfies three conditions. So first condition is the skew symmetry. Skew symmetry. So you take, so this bracket is denoted by a couple of usual brackets. So bracket of A and B, and bracket of B and A are not just equal to minus each other, but they're also related by the flop of the tensor legs. So you take the tensor legs, you switch them, and you take this. Second condition is now you can give the definition of Leibniz rule. Leibniz rule is very natural. You can just give it as usual. When you have three arguments, A, B, and C, and here you have, B bracket of A and C plus A, B multiplied by C. But here I'm using the exterior bimodal structure. So if you now compare this condition with this, you'll see that when you take A, B on the left and take its bracket with C, then what you get will satisfy the same condition, but now with respect to the internal structure. So have A times B comma C internal plus A C B internal. So you see, they do not intersect, and that's very convenient. Finally, the most probably delicate part is the Jacobi identity.
Transforms internal to external.
Yeah, precisely. That's precisely the idea behind this definition. It's pretty ingenious, I would say. So Jacobi identity looks as follows. First of all, when we have A and a tensor product of B and C, we define left double bracket of this form just by taking the bracket of A and B and tensoring it with C. So the result belongs to the tensor cube of A. Now, in terms of this structure, you can define the Jacobi identity as follows. Have A, take B and C, and their double bracket is in a square. Right? A square is tensor square. So you take the left action here. Then you do the same thing. You take B, so take CA, take left here, but there is one thing you need to do. You need to permute the tensor X. This, now you take the cycle 1 to 3 and you permute the tensor X with respect to this. And the last term is again tensor, but now you take the opposite cycle, 1, 3, 2, t minus first, so to say. And you take C, comma, AB, I think, right? And this should now be equal to 0. That's what they call the twisted Jacobi identity. So Vandenberg then moves on describing the properties of this bracket. And it turns out that they exist pretty well, curious analogy between this construction and the standard Poisson brackets. In particular, he defines so-called the space of double derivative. So first of all, he defines the space of double derivatives, double vector fields, derivatives of A. It's again a map from A, space of maps from A to A tensor A, which satisfies the Leibniz rule with respect to the outer bracket, the outer module structure. So UAB is equal to AUB plus UAB. So this is what they call DA, double, space of double derivatives. Now, again, due to the internal structure which survives, this space is a bimodal. So you can now use this internal structure to define polyvector fields. Just take the exterior algebra of this bimodal with respect to the internal model structure. Double polyvector fields.
What is the action of A on A tensor A?
Sorry?
What is the action of A on A?
There are actually the usual. We multiply on the left and on the right. I mean, here, this is equal to U B prime tensor U B double prime. And so you multiply here. And here you multiply on the right. But they still survive the internal structure. And you use this structure to define polyvector fields. And he goes on defining the analog of 9 Harris brackets. And even proves that up to certain conditions.
I think that this object needs to be explained. I mean, external product of bimodules. How do you...
Just this, I think, as far as I can understand. You have bimodule, you take. So first of all, you take the tensor product over. I really want, unless I have made a mistake. I think he doesn't actually. Let's first do it with tensor product. So tensor product is easy. You just take. Now. Yeah, I think it is. You cannot actually go further, deeper into the skew symmetry here. You actually can speak about skew symmetric part, but let's just to be on the safe side.
So A is not commutative, right?
Not commutative. Yeah,
As in super
it's not commutative. It's not neither. It's neither commutative nor super commutative. It's nothing. It's just it can be even the algebra of matrices, for instance, for anything I care about.
Wedge is not clear what wedge is.
Yeah, so wedge, let's admit it. You can actually speak about skew symmetric part of this, but you don't have wedge product, so let's skip it. Yeah, it's true.
But then not clear what would be 9 highs.
Well, I actually I haven't prepared this, but you can define it definitely. It's not an easy thing. You need to work a little bit. Yeah, I can give you a reference. It's in Vandenberg's paper. So it's Michael Vandenberg. The title of the paper is pretty simple: double Poisson algebras. Double Poisson algebras.
Gosh, one moment, but even when we speak about tensor product of bimodals, so we
Yeah, left and right.
tensor product is between the right and left
Yes,
structure.
yes,
In this-
precisely.
Okay.
So you go take the left product on the left, the right product on the left, and go to yes. Yeah, that's true. That's a little bit. Yeah, it's not so simple as it seems. He even then he proves that he doesn't prove that every bimodal structure is induced by a bivector of this sort. So he actually defines bivectors which are in, let's call it D of A, D dot of A, D dot of A, D2 of A. So for every bivector here, you can actually define a kind of double Poisson bracket. So namely, you do the following. You take first.
What is bivector? No symmetry again.
No symmetry. Yeah. You begin with no symmetry. You take so it is actual an element of the form D1 tensor D2, delta 1, delta 2, delta I is in there in this dA, D of A, which we have defined, dI. And then you, let's call it R. So then you take, so you first define D A B R tilde as I think it's delta 2 prime, I think, of B delta yeah, I think I just to be on the safe side, let me take a look at this formula. I really need some prime, double prime, yeah. B, and here you have delta 1 double prime of A tensor delta 1 prime of A delta 2 double prime of B. Yeah, like this. So now this satisfies the Leibniz rule, but it's not skew symmetric yet. So make a skew symmetric. Primes is as follows: delta of A is delta prime of A, just like here. Tensor. That's what they call Switzer notation. It doesn't mean that we have a decomposable tensor. There should be a summation sign here, but it's suppressed in this theory. So you have this formula. It satisfies Leibniz rule. It's not skew symmetric yet, So you then make it skew symmetric just by somewhat a little bit by degree, just by adding the usual minus the twist of the opposite, BA, like this. And now it will satisfy the Leibniz rule and also be skew symmetric. And finally, we need to think about the Jacobi identity. And the Jacobi identity follows from the Nienhuis property, but not vice versa. It's not one-to-one. It's also interesting, and I'll need this just a little bit very soon, that Vandenberg proves the following theorem. So first, let omega of A denote the kernel of the multiplication map from A tensor A to A. Okay. It is again an A bimodule with respect to the exterior multiplication. By definition, A is smooth. Non-commutative A is called smooth. It actually is, I think it's the definition first given by Quillen and Kunz. If omega A is projective bimodal. Projective A bimodal. So, and now this, yeah, finitely generated. Yeah, I don't remember if actually he needs this finitely generated or not. I don't remember this condition if he actually. It should be, but it should be. It should be. Yeah, it should be. It should be. Finitely generated, but in most situations it is. It's almost.
A is finitely generated.
A is, yeah, we always assume that A is finitely generated because we work with representation of spaces over A as a bimodal over A. It's finitely generated as a bimodal over A. It's I don't know if it is always true. It's not probably always true finitely generated by, but
In commutative case, it should be.
In commutative case, it should be. But yeah, but in cases which we are going to, yeah. In cases which we are going to consider, it will hold on the nose. We will again in finite dimensional case, if A is finite dimensional, there is no condition of finitely generated at all. Yes.
Why terminology?
Sorry?
Why is this terminology?
Oh, really? So it's probably it comes from analogy with theory of schemes, I believe, because this is a non-commutative analog of the space of differential bond forms on the space. So if A is regular,
it should be good duality between derivations and one forms. You see?
Yeah.
In formal smoothing.
So the differential forms in commutative case. In commutative case, if A is the algebra of regular functions on a variety, then this is called the forgot the name, not Dolbeau, but what is this? Keller differential forms, Keller differential bond forms, and being projective means that actually it is at every point locally it is free over them. But in non-commutative case, we still have this, and we just give this definition. It's just the definition. One can prove that in cyclic homology, this is actually a good property. You can use it to define the resolutions of your space and so on. So Quillen and Kuntz, they actually draw this analogy pretty far. They gave the definition of some X complex when this works with cyclic homology. So it's a very long story.
I think that they introduced this with Berg complex resolution.
Yeah. They actually gave this. They use it to define the X complex, and they use it to prove there's some definitions of cyclic homology, very similar to the definitions of in algebraic geometry. Okay. Now, a theorem due to Vandenberg is as follows. If A is smooth, then all Poisson brackets are induced from elements of D2 of A. Actually, not just Poisson. Actually, they give you the definition of general double bracket. And all double brackets. So double brackets means that you just omit the condition of Jacobi identity. And what remains, he calls the double bracket. So he proves that all double brackets are induced from 2 of A in this way. Okay. So what I'm going to talk about, I'm going to give a couple of examples which were obtained by my student and myself last year. These examples are not very well. They're not very hard. Not hard at all. They're very low. They're very simple, in fact. But the meaning of them, they maybe not importance. I wouldn't say they are important, but probably the interest which they can induce is due to the fact that so far, almost all the examples that I know of were for infinite dimensional algebras. Finally, generated by infinite dimensional. And the algebras which we are going to talk about are finite dimensional. So they will be very small, in fact. In infinite dimensional case, you can actually define your bracket by defining it on the set of generators. You choose set of generators, and then you look for the conditions that the corresponding brackets should satisfy. If these generators are free, then you can actually take almost any right-hand side. So if you have your generators EI, EJ, then you just put anything on the right-hand side, more or less, something, and you are done. If, in the most cases, even if they are not free, but the relations are simple, like this algebra is commutative, you still can obtain something pretty nice by pretty little cost. But if your algebra is finite dimensional, then satisfying the Leibniz rule becomes a pretty serious problem. For instance, if you take a somewhat naive point of view, which we actually tried to do at first, and take algebra A to be just a matrix algebra. of over C, I don't know, over complex numbers. Then, if you write down all the equations, there will be like, I don't know, d to the 4th power equations, how about so? So there will be d to the 4th power variables. And about the same number of equations. When I say variables, actually even more than that, because if you take generators Eij, EPQ, and then of course you try to write down the right-hand side in terms of this, in the same term, in terms of the same generators. You see there will be d times to the 4th times d to the 4th, d to the 8th. Now, d to the 8th equations, variables. Some of them are pretty simple. Some of them are pretty simple, so it allows you to cut down the number of equations, I think twice, at least, probably. For instance, if you change the order of I, J, and PQ, it amounts to changing the order of these two arguments. Then what you get will equal to the same thing up to the sign and up to the change of tensor x. So it looks a bit like this: E, P, Q, I, J, A, B, C, D is equal to minus phi I, J, P, Q, C, D, A, B, and so on and so forth. So if you try to do this by brute force, you will get stuck even in the case when d is equal to 2. So what we did, we actually we did the following. So let us first take this example. Example 1.
But if you do it for d equal to 2,
Sorry?
if you do it for d equal to 2,
Yeah.
what is careful counting of equations? Is it actually overdetermined?
I think it's overdetermined.
And did you compute like something about the ideal, the generate?
So I'll show you what I'll show you the result. And we didn't actually go so far as to define the ideal, because it turns out that even in this case, the solutions of this case are in one-to-one correspondence with the solutions of so-called associative Yang-Baxter equation, which is pretty.
Natural, yes.
I don't understand why this definition is how it is differ from the usual R matrix definition.
So this definition, I didn't say anything about.
It's the same.
Where? What do you call?
It's not a
The
definition,
definition of
it's just
this
decomposition
double-
by basis.
Double. It is just
Yeah,
usual
sure.
R matrix form of R matrix definition.
Oh, you mean the Jacobi identity? Yeah.
No, I mean this.
Yeah. But first we need to show that all Jacobi identities, all double Poisson brackets are of certain form. So that's what we need to do. After this, actually everything boils down to the Jacobi, to the Yang-Baxter equation. So I don't claim that it's pretty hard, but I just first we need to cut down the number of different possible solutions, because in fact this is not yet our matrix. At least I don't see. Not what I would mean. What I call it, Jan Baxter. It's smart, but it's well. I'll show you what I mean by our matrix first. Yeah.
What is the module omega for the algebra?
Yeah, that's precisely what I was going to tell. So the claim is A is equal to matrices D of C. So the claim is that it is smooth, as one can expect. Well, the proof is pretty simple. You just consider this. I told you that omega 1 of A is equal to the kernel of A times A into A, that multiplication, right? So you have an exact sequence of the form 0, omega 1 of A, then you have A times A, then you have A, and then you have 0, right? Now, when A is equal to the matrices, this is actually a projective module. And this is not just projective, it is just trivial, it is free. So since we have an exact sequence, this will also be, well, projective. It's this exact sequence splits, and then hence this is also projective. If this is projective, this is free, so this is also projective. So this is projective by model. And when A is matrices. And we can use Vandenberg's theorem, which I already announced. So by Vandenberg's theorem, everything is determined by Vandenberg's theorem. Everything is determined by maps delta from matrices to the tensor square. So C. Now, so this is maps which satisfy the Leibniz rule. So the space of
You say that right hand side of the vector sequence A is projective, but isn't it free?
it is not free as bimodule, as projective as bimodule. As bimodule, we were speaking about bimodals. It looks like free, but it's not free. It's projective, and it is the case for the algebra functions. So for the matrices, in case of matrices, it is, yeah. Okay. Now, the space of all derivatives from some algebra with values in some bimodule is determined by Hochschild first cohomology. So H1, we need to consider H1 of matrices D with coefficients in C with coefficients in, well, this. Yeah.
Did we assume from the very beginning that A is unitary? Yes.
Yeah. It's not actually very important. We can work, the same definition works for non-Newtonian algebras as well. Of course, it's not very important. All the definitions hold for non-unitary, but all my examples will be with unitary matrices, algebras. So this is actually, as one knows, this equal to the space of exterior or outer derivations of this algebra A, which is space of all derivations of A with coefficients in M in this bimodal, modular the inner. And that's on one hand, that's everybody knows from Hochschild cohomology. On the other hand, this algebra of matrices, as I told you, is Morita equivalent to the ground field itself. So the corresponding cohomology is equal to the cohomology of the ground field, which is trivially equal to 0. So we see that all cohomology, all the derivatives, all the derivations of matrices with coefficients in whatever bimodal, in particular in this bimodal, are inner. So they're given by commutations, by commutators with certain elements in this bimodal. It follows immediately that all corollary all double Poisson brackets a la Vandenberg are induced. Let's call it like inner. That is induced from elements R in the exterior square of A, but here I take an exterior square in the usual, naive sense. So A is a finite dimensional vector space, obviously, so I'll just take the exterior square of this finite dimensional vector space. And so if R is equal to, say, X tensor Y, then okay, of course, it should be also minus Y tensor X, which I omit, which I just omitted. Then the bracket AB X tensor Y is equal to BX A tensor Y minus XA tensor B, Y B minus BX tensor A Y plus X tensor A Y B. That's a corollary of this. So all.
Should you also add 4 more terms?
Sorry?
Should you add 4
Yeah. If we have this, then we need to add 4 more terms precisely. Actually, even we can have even more than 2 terms because actually we work with a generic element in the tensor square, in the exterior square. So it can be some element of the tensor. But for every element, we have
By
this.
the way, if you take R only equal to the half of it, X tensor Y, then probably you can extend your theory to so-called modified brackets.
I think so, yes. I think so.
Goshen, where C is essential in this?
It actually can work with over arbitrary characteristic zero field. Also, I think you don't even need to have it algebraically closed. If you want, but if the field is algebraically closed, then you can actually have a similar result for arbitrary semi-simple algebra. Yes. If you have a
where does it?
algebraically closeness, we need algebraic closeness if we want to use Wedderburn-Artin theorem. We work with semi-simple algebra. We want to represent it as direct sum of matrix algebras. For every matrix algebra, we have this, and that's actually how you prove it.
By the way, it is just a curious remark. This example immediately gives example that the double bracket of A with itself is not 0. In contrary to usual Poisson.
Yeah. Yes.
Specification of this opposite structure. I mean, if you take AA here, you are feeling non-zero.
Yes, precisely. But this is 0. On the other hand, this is 0.
This is 0.
This is 0. This is important for the next example, which I'm going to talk about. So the next example is much less. It's not very hard either, but it's much less simple. So yeah, but I haven't yet done with this example. So we have this corollary, but I haven't yet said anything about the Jacobi identity. So Jacobi identity now, as I claimed, follows from the associative Yang-Baxter equation for R. So R should satisfy the associative Yang-Baxter equation. So it means that to classify all double Poisson brackets in matrices, we need to classify all solutions of associative Yang-Baxter equation, which is not a simple thing at all, I believe. More or less, it's more or less equivalent in case of matrices.
It's even for 2 times 2. It's not.
Yeah.
Not easy.
It's not easy even for 2 times 2 precisely. I would say that, but what is interesting it is that when you work with non-matrix algebras, but with some more general algebras, you also can define inner double Poisson brackets by precisely the same formula. In that case, you really don't need the associative Young-Baxter equation. You can still write down this associative Young-Baxter equation in that case. And of course, if your element R satisfies the associative Young-Baxter equation, then your double bracket will be Poisson, but not vice versa. There exist examples, and I'm going to show one of them right now, when you don't have the associative Young-Baxter equation, but the element is still, but what you obtain is still double Poisson. So it's a little bit more delicate. So that's example one. And the second example is even simple in some respect, but not very easy either. So example is
Just to finish this example, back to d equal to 2.
yes. So you need to.
When you reduce things,
I mean, you need to solve the associative Young-Baxter equation. I don't know if it is always possible. I'm going to give you a simple example where we actually work with 2x2 algebra matrices, but with upper triangular 2x2 matrices. So if we work with 2x2 upper triangular matrices, it gives you a three-dimensional algebra, which is not semi-simple, because it has it is not even equal to sum of something. It has the divisors of zeros inside. So let A be equal to the space of matrices A, B, 0, C. A, B, C are complex, are real, doesn't matter. Let it be real. Let it be real. So, well, you know, E0, this matrix. Then we have E1, and that's E1. And finally, we have E2, 0, 0, 0, 1. And now, since the dimension is 3, we were able to finally solve all these equations. It's not an easy exercise. It takes, well, a couple of pages of computations. We need to take.
Did you use the Sokolov classification for?
I think Sokolov actually works with, maybe I'm wrong, but as far I really need to take a look more attentively. But as far as I can understand, the matrices, maybe I need to look better.
I think that he has 19 classes. So
maybe. But we also obtain something which doesn't look like inner. There's something which doesn't look like inner. We really need to be more careful, but so there are a few identities which makes the whole solutions easier. So first identity is as follows: E1 plus E2 is equal to 1. And since, as I explained, this is always 0 for all elements, it follows from the Leibniz rule. Seem very straightforward way. It means that this E1 is equal to minus a E2. So we need only to set it to this actually this helps a lot, because now we only need to consider, well, 6 equations instead of 9. Then we also have symmetry plus symmetry, which allows you to cut down the number of parameters. And so there will be like 6 parameters, and after some work we were able to cut down their number even further, and I'm just going to write down the finite result which we obtained. So theorem. So it's again Abner and myself. Here's the formula. So there will be 3 parameters. alpha, beta, and gamma in the ground field. Okay, let it be K. Any field actually works. So then we have three non-trivial brackets. First, the most complicated is as follows: is E0, E1 is equal to alpha 30 times E0 times E0 plus beta 1 tensor E1 minus E1 tensor E1. It's actually, if you write down E1 as 1 as E1 plus E2, it will probably be easy. I don't know, but you can keep this for a while. Plus gamma E0 tensor 1 minus E0 tensor E1 minus E1 tensor E0. That's first. Second non-trivial bracket is E0, E0, as Volodya has claimed. In this case, the repetition of argument does not entail the fact that on the right-hand side we have 0. We have beta 1 tensor E0 minus E0 tensor 1. And finally, we have E1 tensor E1 is equal to gamma E1 tensor 1 minus 1 tensor E1. Okay. So all the rest can be obtained from this property and from skew symmetry. All the rest follows by this.
With arbitrary alpha, beta, and gamma.
Yes, one more condition. So this only provides the Leibniz rule. But if we want Jacobi identity as well, we need to Jacobi identity is equivalent to gamma squared plus alpha beta is equal to 0. So it gives us kind of two-parameter surface. Yeah, cone. Yeah, cone. I don't know if this means something, but it's just a kind of result of brute force computation. It is not very. Yeah, just did this one after another, eliminating all the terms in these equations.
For arbitrary k.
Yeah, I don't think.
What is HR?
Sorry.
HR in the theorem, radiation.
That's my student. You know, Abner Hernandez-Rodriguez.
Okay.
He's Mexican, but he actually is a student of. He now is in high school of economy. Yeah. Okay, I think it is also probably interesting what kind of Poisson structures this construction induces on representation spaces. It is also quite, I think, intriguing. So I'll give an example here as well. So first of all, let me describe the representation space. Sorry?
Is it smooth in this case?
No,
Right.
it's not so much simple. I think it is not smooth. No, it's a good question. I didn't think about this. I think it is not smooth. I didn't think this very carefully about this. It's just, yeah, it's a good question. Didn't think about this
That's
properly.
even more interesting. If it's not smooth, how you check it?
Homology. I think Hochschild homology is detected.
If in this case, after triangular matrices, the module A is
It's well, as far as I can understand, the smoothness is determined by the Hochschild homology. of the algebra with coefficients in this bimodal, I think. So something like that, as far as I can remember. I don't remember this correctly.
It's a question
I don't
of
think it's
also notion of dimension. What
Yeah, yeah,
you
yeah, yeah.
Understand it. Dimension.
Yeah.
no, you talk about things. So we talk about just projectivity. So of course, if you
Projectivity of bimodal. So if this bimodal is projective, then certain cohomology is trivial.
precisely one direction.
Yes.
But now you would like to prove it is
Yeah. I mean, if this cohomology is non-zero above certain dimension, then it is non-projective. That's what I would say.
Probably the condition is that H1
Mhm.
of Hochschild in the with coefficients
In
A
this
dash
bimodal,
A
yeah.
and H2 equal to 0. That it's
I don't. Yeah.
more than enough to
Yeah. I also think I don't
that's necessary. That's not sufficient.
for smoothness. Yeah. It's necessary for smoothness.
Necessary,
But
not sufficient.
uh,
So how you determine non-projectivity?
hmm. Well, you're right. There exist lots of sufficient, but not necessary and sufficient. I don't know if there exists any necessary and sufficient condition in this situation. There probably are. I need to take a look. Actually, this part of noncommutative geometry is pretty fascinating, but I don't think it has been studied extensively enough. I actually don't know if there were many papers after Kunz and Quillen. Probably Volodya knows. Were there many papers after Kunz and Quillen? I know that they introduced this, and this was somewhat. It was not very popular because they actually just gave another way to compute cyclic homology, pretty complicated way. So people involved in cyclic homology didn't like it very much indeed, because it was a hard way to obtain something they already knew. I don't know. I don't know if there exist many good answers to your question, therefore. Yeah. So I need, okay, let's speak a little bit about representation spaces. So I'm only interested in case of two-dimensional representations of this algebra of upper triangular matrices. And in this case, one can give a pretty good and simple and geometric description of representation space. Let me write it down. So there are three matrices. You need to introduce three matrices, E0, E1, and E2 in 2x2 matrices. They should satisfy certain naive conditions, like E0 square should be equal to 0. And that means that in 2x2 case, it means that the Jordan form of E0 should be like this, right? If its square is equal to 0, it should look like this.
Or maybe bigger matrices.
Huh?
Or maybe bigger matrices.
I'm speaking about 2x2 representation.
Okay.
Only about 2x2 representations.
Gosh, maybe not E, but something else.
Okay, capital E. Yeah, capital E will do. Yeah, I think. Yeah, I'm speaking about 2x2 representations, so that's pretty simple. Just to
You
keep.
represent 2x2 matrices by 2x2 matrices.
Yeah. Yes, somehow. But how many different ways to represent it there are? And the answer is pretty interesting. So, first of all, so I'm not going to give all the details. I just want to explain that the rank is equal to 1. Rank of E0 is equal to 1. It means that E0 is equal to the product of certain x1, x2 by y1, y2, right? A matrix product like this. Every rank 1 matrix has this form. That's all. Now you have 4 coordinates. I can write down in terms of these coordinates everything. They also have conditions like 0 times E2 is equal to, I think, E0, and E1 times E0 is equal to E1, sorry, to E0. And then you also have conditions that E1 times E2 is equal to 0, right? If you write down all these conditions, then you will see that representation space can be described by by 6 parameters: x1, x2, y1, y2, parameters with coefficients, sorry, in the corresponding field. So it can be complex or real, whatever you prefer. If you work with complex representations, then they should be complex. Z1, Z2. And the conditions are as follows. So first of all, x and y should be perpendicular. Right. Second, x1 is the norm of x vector is equal to 1. Right. And x and z should be perpendicular. Right. That's all, more or less. So this means that you actually work with points on a circle. This is perpendicular. That means that y lies in the tangent space of the circle, right? And so does z. So altogether, summing up, so since oh, I forgot to say that this is not perpendicular, is equal to 1, sorry. So this is perpendicular, this is perpendicular, this is circle, and this is, it is also almost perpendicular, but a little bit shifted. So altogether, this space is three-dimensional. The space is three-dimensional. It has dimension 3, summing up everything. And if you take the simplest Poisson, double Poisson structure, which I described, which is equal to E0, E1 is equal to alpha, E0 and the E0, and all the others just vanish. You can do this, right? Because actually the condition was gamma squared is equal to alpha times beta is equal to 0. So if it is 0 and beta is 0, we can take arbitrary alpha, and you're done. Then the Poisson structure will look as follows. So the bivector of Poisson structure will look as follows. There will be 3 parameters, lambda, mu, which describe y. So lambda is parameter along the straight line containing y. Mu is parameter along the straight line containing z, right? And theta is the parameter which determines the point in the circle. So there are 3 parameters: lambda, mu, and theta. And the equation will look like as follows. Lambda and mu will commute by a times lambda square, and all the other zeros. All the others are 0. So it gives a non-trivial, although pretty simple. So I think it's probably better to put alpha here. Alpha is this, the same parameter. It's just some notation which we used. We changed it for some reason. I don't remember for what we changed it. Yeah. In dimension, if you take representation rank 3 representations, you have a pretty similar picture here. In this case, the dimension is equal to 5, I think. The dimension is equal to 5, and not to 6. In this case, you work with a sphere. You have a point on the sphere, and you have 2 points in the tangent plane to the sphere, 2 points. And the matrix of the Poisson structure in corresponding parameters will look like block anti-diagonal of rank 4. So here you have zeros. You have 2 columns and 2 rows of zeros. And here you have a matrix of the form A alpha square so alpha A is again a parameter. So yeah, this is probably why we changed it from alpha to A, because alpha and beta were coordinates in these situations.
A is the algebra.
Yeah, precisely, probably. So it would be lambda, I don't know. Phi, yeah, phi. Okay, so it would be xy, phi, so phi x square, phi xy, phi xy, phi y square. So x and y are coordinates on this space, right? Yeah. And that's all, I think. So there are 4 coordinates. There are 6 coordinates. Again, there are some things explained. There will be a sphere here. There will be 2 spherical coordinates, phi and theta. Spherical coordinates. There will be 4 coordinates in the planes perpendicular to the radius. So these x and y are coordinates in one of the planes, as far as I can remember. So it looks pretty strange, you see. It's anything but totally trivial. And what to do next is a good question. I still don't know. There are lots of things you can do further. You can consider other examples. You can think about integrable systems in terms of these in terms of these coordinates. Because you see, we work almost on cotangent bundle of a sphere. So this representation space looks almost like a cotangent bundle of the sphere with some extra coordinates which do not interfere into this at all. But these coordinates means that this is actually a Poisson structure, not just a symplectic structure. So we have some Poisson structure on the cotangent bundle on the sphere, which looks pretty interesting. And what kind of integrable systems there can appear? It's a good question. Okay, I think I'm done here.
Okay,
I'll stop here.
Thanks a lot. Just one question. When you spoke about Young-Baxter, you meant classical?
No, associative.
So,
Associative Young-Baxter.
Конечно.
Associative Young-Baxter looks like this. I'll try to write it down up to, it's 1/2 of classical. I'll write it down in terms of up to the sign. So R12 multiplied by R23 plus R13 multiplied by R23 and minus, I think, R23 times R13, maybe, sorry. No, something I'm missing something.
If you take minus, you should take one
Yeah.
disorder.
Yeah, precisely. I keep forgetting this. 1, 3. So first of all, 1, 3, 2, 3. That's 1, 3, 1, 2. Sorry, 1, 2. So here you have 2, 3. 2, 3, 1, 3. And when I have minus, it's 1, 2. It's hard to remember. 2, 3. That's Now the product is just a product of the algebra in the algebra. This is an element in A tensor A, right? You have another element in A tensor A. You insert 1 here and take their product. So this is R2, 3, and this is R1, 3. You multiply them likewise along the tensor legs.
Well, thanks a lot. Questions? Remarks?
Any remarks during the talk?
Yes, a lot of remarks during the talk, but maybe
Criteria of formal smoothness that x2 over A tensor A equal to 0. It's a Kontsevich and Rosenberg.
Yeah, maybe.
Criteria.
It's actually again in Quill. It should be. It should. No. Alexander.
False,
Да, я
then
его
it's smooth,
хорошо
right?
знаю.
Рок, что он умер, конечно.
Володя, if this false, then it's smooth.
It is if.
If and only if? Really?
Yes, it's a 4 criteria. They
Well,
give-
if the audience
I really need to take a look in Kunz and Quillen paper to answer this question. I'm sorry. They also give several equivalent statements, Kunz and Quillen. I just don't remember them.